In this video, we're going to look at some additional organometallic reactions. Let's look at this first one here. Hypothetically, it should be possible to take an R- equivalent, like an organolithium, and why not just use it as a nucleophile in an SN2 reaction to couple two carbons together like this. Well, in reality, this reaction doesn't work very well. The problem is that the organolithium or Grignard reagent is an extremely strong base, so there's serious competition with E2 reactions. And there's also a problem in that these reagents are extremely strong reducing agents, and they can move, just transfer electrons, and unusual processes start to happen as a result of that. This works to some extent. It's a very old reaction called the Wurtz coupling. There's an obvious pun here, right? It doesn't work that well. It's one of the Wurtz reactions in organic chemistry. Okay, sorry, just had to get that out there. All right, if you want to do this, you can do it if you just change the metal from lithium or magnesium to copper. All right, so if you take two organolithium reagent equivalents, or 2 moles of an organolithium reagent, and a copper 1 salt, it has to be copper in the +1 oxidation state. And our counter ion here, in most cases, is chlorine, bromine, iodine, or cyanide. This generates this reagent, known as the Gilman reagent. Okay? And with a Gilman reagent, you can now treat it with an alkyl halide, bromine, iodine, or tosylate. Now tosylates are okay since this is the coupling partner. And this will, in fact, give you your coupled product right there. The question you might have here, and this is a good question as far as like economy goes, if there's 2 of these here and only one of them is showing up in the product, what happened to the other equivalent? Okay, well, it turns out that it's wasted. Okay, it's going to do some unproductive process, and you have to, whatever it ends up as, you have to just dispose of it as waste in the proper way. Okay, so this is one of the big limitations on this Gilman chemistry, is that you're wasting 1 mole of your organolithium reagent. All right, Grignards are a little bit less reactive, and it's possible to do a catalytic coupling here. Okay, so if you take a mole of Grignard and an alkyl halide or tosylate, and now just a catalytic amount of copper halide, you can get the coupled product this way. So this is a little bit more efficient. This doesn't waste a mole of reagent. Okay. All right, so let's complete some reaction equations here. There's some funny stoichiometry in this business too, if you think about it. It takes 2 moles of lithium to make an organolithium, right? And then one of them is going to get wasted, and then it's going to take 2 of these organolithium reagents to make your cuprate. Okay, so the stoichiometry is a little bit funny if you follow it all the way through. All right, so let's look at a few examples here. So let's complete these reaction equations. All right, in the first one, we're going to treat it first with magnesium ether, then CuCN and an iodide, of course, in step 1. We are indeed making our Grignard reagent. Okay, and now we're going to do the coupling reaction. So this is going to couple this unit okay, minus the chlorine, to this unit, okay, and they're going to join right there, like so. And when we draw the product nice and neatly, there it is, okay. All right, in the next one, the cuprate reagent has already been made, so we don't see any part of this equation being used to make the cuprate, so we're just taking an alkyl halide and we're reacting it with the cuprate. What we see here is we're going to transfer an ethyl group, and it's basically just going to replace the bromine right there, and there is our product right there. I didn't say this before, but this reaction goes with retention of configuration. It's clearly not the SN2 reaction because it works with a halogen at sp2 carbon. It's mechanistically quite complex. So you can still use the vinylic halides in this cuprate coupling. All right, and the last one, we're taking a cyclopropane ring, 2 lithiums are going to make 1 mole of cyclopropyl lithium. Okay, and now we're going to take this 1 mole, and we're going to take half a mole of copper iodide, and we're going to treat it with this halide right here. So what's going to happen is we're going to just make a union between these 2 carbons right here, and this is our product. Now, because of the stoichiometry, the best yield we could possibly get, if we're looking at the yield relative to cyclopropyl bromide, is 50%. Okay, or we would look at a 50% yield as being 100% yield. It's a way to look at it. Okay, because we're going to have to waste one of the cyclopropyl units in this reaction. Okay. Another important reaction of organometallics is carbenes. And we are going to, even though carbene is divalent carbon, where's the metal? Well, what we're going to find is that an organometallic is our most likely source of a carbene. All right, so the most important reaction of a carbene, or divalent carbon here, is its reaction with an alkene to make a cyclopropane. This is a concerted, meaning one-step process, and it goes with retention of configuration, which means that whatever configuration of the double bond we had in the starting material, we'll have it in the product. All right, so we don't usually think about the geometry of small cycloalkenes like this, but this is, of course, a cisalkene. So the product we would end up with would have the 2 hydrogens in a cis arrangement. Okay? If we want to look at the mechanism, it's not really much of a mechanism. It's just a concerted electron reorganization. Okay? The arrows move like that. This is known as a helitropic reaction. It's like the Diels-Alder in that it's a paracyclic reaction. To fully understand it requires a higher order molecular orbital analysis, which we're not going to do. All right. Notice how I've drawn this structure here where we can think of a carbene as being like a positive charge and a negative charge on the same carbon. Okay, so here we have the empty p orbital, which we've of course associated with a carbocation. And here we have the filled sp3, sp2, which is kind of like a carbanion, right? Lone pair. All right. So that's why we are using this analogy. If you look at the arrows, I have one arrow using the lone pair as a nucleophile and the other using it as an electrophile, accepting the alkene pi electrons in the second arrow. So here's the first arrow, here's the second arrow. I don't know that they necessarily go in that order. All right. In addition to a carbene, you can also have a type of reagent. It's known as a carbenoid. Okay. The carbenoid has an electronegative, giving a partial negative to the carbon, and it has an electropositive element, giving a partial positive charge to the carbon. So here you see again this relationship to this imaginary structure right here. Okay, so if you have a metal and a leaving group on the same carbon, it's equivalent to, or its reactivity is equivalent to that of a carbene, and we refer to it as a carbenoid. Okay, the metal in this case usually is not lithium or magnesium. It's a little bit too hard to put those there while there's a halogen. Okay, so it leads to kind of a instability. So our organometallic reagent, or our metal, is usually zinc. All right, so here's a reaction called the Simmons-Smith reaction. In the Simmons-Smith reaction, we're going to take zinc, and it's activated with like 1% carbon to kind of disturb the lattice energy of zinc and make it a little bit easier for a zinc atom to come out of there. And when you have these reagents, they combine to make this compound, which you see is a carbenoid, because it has a carbon-metal bond and a carbon-halogen bond on the same carbon. Okay, so that makes it a carbenoid. And at room temperature, this will react with alkenes to make cyclopropanes. Okay, so reaction with cyclohexene makes this. Okay, that's the only stable ring fusion for a 6-membered ring fused to a 3-membered ring, really cis, like I show there. However, if we take a non-cyclic alkene, we can have two different geometries. So here, we're taking the trans, and what we note here is that we get the trans cyclopropane. Okay, when you take the cis 3-hexene, like here, you end up with the cis cyclopropane as well. Okay, so this, again, it's just a trait that we associate with syn addition to the carbon-carbon double bond. We've seen this before with making epoxides and hydrogenation and things like that a long time ago when we studied the addition of things to alkenes. Okay, let's look at a related carbene that's relatively easy to acquire too, and this is the dihalocarbene. Okay, so if you take chloroform or bromoform, these are the only ones it will work with. It won't work with iodoform, and it won't work with CHF3. All right, this is acidic enough so that if you treat it with KOH at equilibrium, it can make the trichloromethyl anion, and the trichloromethyl anion can lose a chlorine to make the species dichlorocarbene. And this will readily add to any alkene that's in the reaction pot. Okay, so here I have cyclopentene, and this is now formed the cyclopropane fused to the 5-membered ring. All right, let's complete, well, we've already completed these reaction equations. So if you take this one here, you'll add the cyclopropane here, and of course the hydrogen that's been omitted from the bond line diagram. ends up cis to the CH2OMe group because that's where they were in the starting material. All right, we're going to take this cis alkene and treat it with bromoform and KOH, and what we find here is that we get the cis cyclopropane. And since our starting material had a cyclopropane and this reaction adds a cyclopropane, it comes to reason that we're going to end up with a product that's going to have two cyclopropane rings in it, okay? All right, let's look at one more reaction that we're going to hold people responsible for on exams and stuff, and this is called olefin metathesis. It was a reaction that's been known for like 60 years or so, but it was kind of not that useful until a discovery in the early 1990s. All right, so here's the essence of olefin metathesis. We're going to take two alkenes, okay, and they're going to be different alkenes. And what we're going to do is we're going to add a catalyst, and when you have a double bond between a carbon and a transition metal, it's known as a metal-carbene complex. Okay, so a metal-carbene complex is required as a catalyst. All right, and when you do this reaction, what we find is that we basically swap the ends of the two dissimilar alkenes, and we end up with all possible combinations, okay? All right, so we end up with an alkene that has an R1 and an R2. We end up with an alkene that has two R1s. We end up with an alkene also that has two R2s. We produce some ethylene. And again, sorry, I forgot to circle the original one that I was talking about, but we've totally placed the system at equilibrium. All right, you may wonder, as presented there, it looks kind of like a crappy reaction, doesn't it? You're getting an awful lot of products. And since it's at equilibrium, not only are you getting the products, you're also getting the starting materials as well. Now we're going to find that we can use this equilibrium idea to our advantage. We're going to look at two cases of olefin metathesis that work very well in a predictable fashion. Okay, so here is the mechanism. All right, the mechanism involves a series of 2+2s cycloadditions, followed by retro 2+2 cycloadditions. And that's how you can very accurately describe what's happening in olefin metathesis, okay? Now, you may recall from back when we talked about the Diels-Alder reaction that the 2+2 cycloaddition we said was a molecular orbital forbidden, or a orbital symmetry forbidden process. Well, with a metal carbene, it involves d orbitals, and you can form complexes with the alkenes. So the orbital symmetry rules are a little bit more complex for transition metals. So we're going to now just assume that the 2+2 is an allowed reaction in this case because of the d orbitals at the metal. Okay, so really a higher question that we're not really going to discuss in this class. This class is organic chemistry, not inorganic chemistry. We do have classes in organometallic and inorganic chemistry here that you can take and start contemplating issues like orbital symmetry for metal carbene complexes. All right, so 2+2, this one, we'll do the 2+2 to make this called a metallocyclobutane. It'll do now the retro 2 plus 2 to produce this. All right. Now, our new carbene complex now has a unit of the alkene there. It can complex with the other alkene. Now we're going to do a 2 plus 2 again. Another retro 2 plus 2. Okay. And when this releases the alkene from the complexation, we're getting now the mixed alkene. All right, so this process, I've stopped it here, but it keeps on going. Okay, there should be many, many more equilibrium arrows for all the species that are in solution. All right, so we said it's at equilibrium, and remember, reactions at equilibrium are controlled by thermodynamics. So, if our starting alkene has angle strain, like cyclobutene here, okay, and this is the most important, or this is probably the most commonly used catalyst for olefin metathesis. It's called the Grubbs Catalyst second generation. We're just going to call it Grubbs Catalyst, and the most important part of it is the carbon-metal double bond right there. All right, so if our alkene has a lot of angle strain, like cyclobutene, okay, we can release that angle strain by doing an olefin metathesis that's just going to put multiple units of cyclobutanes together here, and this is going to make polymer. And this is called the ring opening metathesis reaction, or the ROMP reaction. ROMP means something very different to an organic chemist than it does to someone out in society. Okay. All right, another very useful example is ring closing metathesis, and this is kind of not completely thermodynamic, okay? It's kind of a entropy-driven process because it produces ethylene as a byproduct. Ethylene is a gas, and it leaves the system, okay? And this tends to drive these reactions to completion. So ring closing metathesis is just going to take a molecule that has two alkene groups in it, and we're going to make a bond between the two closest alkene carbons, and we're going to eject the outer alkene carbons. And we're going to eject them as ethylene, okay? All right, so if we treat that compound with Grubbs Catalyst, we're going to make dihydrofuran and ethylene. As long as the ring you're making is thermodynamically relatively stable, this reaction usually goes pretty well. It's been used in some rather complex molecules. I show here this anti-cancer agent, uprolide G acetate. Okay, so one of the key steps in the synthesis of this compound was to take the ends here and just combine them there with Grubbs Catalyst, and to make now the cyclic product, and just a few other chemical steps would turn it into the actual useful pharmaceutical compound. Okay, let's see, Nobel Prize. Yes, so it's worth mentioning here that this is probably one of the most dramatic examples of success in chemistry. It wasn't until like the early 1990s when Grubbs at Caltech and Schrock at Massachusetts Institute of Technology developed catalysts that you could put in a bottle and ship to people who need it, and then the people making the alkenes could just simply just add their catalyst to their reaction and make them go. So the Grubbs and Schrock the Schrock catalyst is a little bit more complex. It involves molybdenum, but it tends to be a little more reactive. But what I'm saying here, I guess, is that after this was invented, it became within 10 years, it became one of the most used reactions in all of chemistry. Okay, so it's kind of revolutionized how people think about synthesizing things. Okay, all right. So we're going to just look primarily at ring closing metathesis in this class. Well, let's see if we can complete a few reactions that involve Grubbs catalyst. Okay, so what's the product of the first reaction and what starting materials are required for the second reaction? So in the first reaction, remember that we're going to take the two closest alkene carbons and we're going to combine them into a ring, and the outer carbons are going to become ethylene gas. Okay, all right, so if you count up here, let's just call this 1, 2, 3, 4, 5. It means that our product is going to have a 5-membered ring added to these two 6-membered rings. All right, so there's our product right there. All right, what's the starting material? Well, remember that this is the bond that you formed. The starting material had 2 additional carbons that were lost as ethylene. Okay? All right. So what we really want to think about is that we really had a product, or our starting material that we required really needed to have no bond between those 2 carbons, and it needed to be ethylene, or needed to have 2 more carbons that are going to get lost as ethylene. So the precursor compound is the one that you see right there. And one of the beauties of the metathesis, or ring closing metathesis, is that it's been demonstrated to be successful in the presence of virtually every known organic functional group. Okay, all right, so I'm going to stop this video here so as to make them a little bit more symmetrical, and the last videos are really just going to primarily have more problems. Okay, so we'll stop this one here.